Green's theorem, 13.4. Very important. Unfortunately, only works in 2D, and the upper dimensions can be in other classes. Stokes' theorem is super important. Everyone who are engineer, you will be working with Stokes' theorem a lot, and that's continuation of Green theorem in the upper dimensions. This is a second fundamental theorem of calculus for vector fields. They say that the grass is greener on the other side, but I say it is Green's theorem on the other side. Well, because today it's all about Green's theorem. Okay, good. That's my friend's job. It only works in 2D. They are analyzed in 3D in upper level course. Unfortunately, we're literally ready to do the next chapter and it doesn't fit into the schedule. I'm very sad. Everyone keep asking, when we hire new people, they ask, do you guys teach Stokes' theorem calculus 3? We're like, no, and that's upsetting. So, Green's theorem is useful. Also works for non-conservative vector fields. Anyway, let's write down the formula. Green's theorem. If F consists of two components, P and Q, and C is a closed curve with the region inside D, inside region D, so closed is important, then there is a formula. The integral you've seen before in your previous homework, integral f dr, is double integral over D, partial derivative with respect to Q, of partial derivative of Q with respect to X, minus partial derivative of P with respect to Y, dx dy. From single integral to double integral, but the idea is that double integral is easier. That's the idea. And the difference is we worked over C, which is a closed curve, right? For example, like this. Instead, we're going to work over D. That is the region inside. But when we talk with areas, volumes, those are double integrals. So it intuitively makes sense that we're moving to double integral over D. And you take the second component, Q is a second component. Differentiate with respect to first variable, minus take the first component, differentiate with respect to second variable. Line integrals can be hard, so that's your homework right now. So this is an easier way, it's a very known way to do it. We're going into easier double integral. Some people just remember this order, Q over X minus P over Y, but actually it comes from the determinant. Determinant looks like this. Now it's ordered nicely. X and P on the left-hand side, Y and Q on the right-hand side. And then, of course, with a cross product, it gives you that. That's the notation. Derivative with respect to X, then P. Derivative with respect to Y, then Q. So then you know how to calculate this determinant, and it gives you the formula. And minus also. Now, minus explained really well as well. Good. Let me know if it's too fast. That's how it looks. It's not like something I just draw it. This is just a nicer idea. Instead of walking on the path, we're moving to double integral using this area. So, in knowledge of double integrals. Example. Let's calculate the integral f dr. F is given x to the 4xy. C is a triangle. And it's counterclockwise. We don't like triangles and stuff like that. And when you did your homework, you already noticed. It's so annoying. To have two different lines is really annoying. So it's just hard to work with lines when it comes to line integral. Here's a sketch, a triangle. So I'll ask you while you're writing, how many integrals we will have here? What do you think? Remember or not, this is the homework that's due tonight. The line integrals, you work on C. You work on C. But to work on C, you need to create R. R is the parameterization, and you have to create it by yourself. Sometimes we give you R, like, oh, this is like t squared minus t. But then if we don't, you have to figure out by yourself. Well, it will be first this one, then it will be this one. So C sub 1, C sub 2, and C sub 3. It will be 3 different lines. That's lots of effort. But that's how the parameterization works. You'll have to distribute it into 3 integrals. This integral will be this line integral f dr will be integral plus integral plus integral. Because it was over c, it will be c1, c2, c3. Yeah, that's too hard. Moreover, x to the 4 and xy, the components inside, are also hard. So when we figure out some parameterization, it will be more raised to the 4th power, then it's going to be product. That also makes it harder. So in general, we see it's a closed path. We don't want to proceed with this pain. It's going to be a pain to do line integral directly. Not only f is complicated, but you need to split the line integral into 3 pieces. And as it says here, ew. It says it here. We're not going to do that. So instead, let's use Green's theorem. Green is the last name, not a color, by the way. Green's theorem. Just like I decided to make a comment. Steps. Basically, step 1 is to know the formula. The formula says integral over C f dr. For the closed path, and we have that. We're going to go into D. So we're going to figure out the D now. That's whatever is inside the C, because we have the region inside this D, inside of the triangle. So we're going to have D. And then, check it out. It's you just need to have to memorize it, but it's actually not too bad. The second component first. Differentiate with respect to first variable minus the first component. Differentiate with respect to second variable. dx dy. dx dy can be changed. That's the creativity part. That's the formula. So the step 1 now to know the formula. Here it is. Let's do it. Either you do it step by step and you first finish in figuring out the derivatives, or you create the limits of integrations right away. I will do right away. Integral. Okay, what is Q and what is P? I have to go back and find it. Oh, here it is. So instead of C, now we're working with D, and D is in whatever is inside of this triangle. So we decide to ditch working on the path. That's the idea. Now, x to the 4 is P, and xy is Q. Let me rewrite it again. So I have f equals x to the 4, xy. But that is also P and Q. That's just names. P and Q can be named anything else. You could name them J and R and so on. But international people name it P and Q, and they stick to that. Why it's P and Q? It's an alphabet. P goes first, Q goes later. But also P and Q capitals are used quite often to name some polynomials and stuff like that. So it's also pretty popular. We don't want to do I, it's reserved, I, J, K, reserved, T for time, temperature, reserved. So it's kind of nice to avoid whatever is usually reserved. So P and Q is good. Although physics majors will disagree. P and Q are everywhere in physics. So it says differentiate first Q with respect to X. So I'm looking at the second one. Oh, let me write down first for you. And I will take xy differentiated prime with respect to x. Does it make sense? Minus, now I'm looking at the first one, and I will differentiate x to the 4 prime, but with respect to y, dx dy. Dx dy, like so. How about limits of integration? They are coming from the picture. Limits of integration are coming from the picture. Here's the picture. You can choose to keep it dx dy, or you can do dy dx. That comes to double integrals, reverse the order of integration. We did that in exam 2 also. So either we're going from this way, from right to left, or we're going from top to bottom. Let me remind you the idea. The idea is whatever you choose to be outside will have numbers. Whatever you choose to have inside, in this case dx, that will be functions. So we just choose any. It doesn't matter, to be honest. Which one do you prefer? Or you have intuition, which one will be easier? Okay, if you don't have preference, let's keep it as it is. But you don't have to. You can switch the order. You can do or dy dx, and it will be pretty simple as well. If I keeping y outside, then y will have numbers. Y is my height. From which number to which number? Y is running up and down, up and down. Number. 0 to 1. Exactly. So outside, I'll put 0 and 1. Now, since I'm done with y, x will be not from a number to a number. Do you know why? If I put x from number 0 to 1, that gives me a square. Because that means I forgot to indicate that not all of this is needed. Because if x is running from 0 to 1, it gives you a square. We need to make sure it's not running from 0 to 1 all the time. Sometimes it's running from 0 to 0.3, 0 to 0.7. How to indicate that? Using functions. So x is running from the bigger minus smaller. It's always like that. Well, I say, okay, running from this line to line in blue. And your job is just to figure out equations for those two. What is the equation for the vertical line?
No, sorry.
Close. It should be x equals stuff, right? Yeah, x equals 0. And it should be something like x equals blah, blah, blah. That's also what helps me, which one to choose. So it's definitely x equals 0. And then the second one you have to figure out, do you know? 1 minus? 1 minus y? Yes, no? Yeah, just set it up by yourself using 2 points. There's a formula if you want. Y minus y0 equals mx minus x0, and there are more formulas. Use any formula to figure out this equation. But it is y minus 1 minus y. So it's running from the vertical wall x equals 0 till this wall y minus y. So we're going to put it there. That's review of exam 2. 0, 1 minus y. Does that make sense? And you can do the other way around. Let me do it in parentheses so you have good notes. Integral, this thing inside, I'm not going to rewrite it. If I want to change dy dx, now x outside is running from a number to a number. Well, x is running from 0 to 1. So it's going to be from 0 to 1 for x. But now y is running from a function to a function. And the function on the floor has a name. Y equals, no, the floor, 0. And this wall can be rewritten as y equals 1 minus x, right? So then it will be from 0 to 1 minus x. And the same, not too hard. So doesn't matter here. You want to change it, just change it. That's parentheses. I'll do or. Finally, let's write it down. From 0 to 1, from 0 to 1 minus y, I'm sticking to the first one. xy with respect to x gives me just y. X to the 4 with respect to y gives me just 0. dx dy. That's a simple integral. Quickly finish that one, and you get 1/6. And this is the answer for the line integral. It is much easier than to do 3 different integrals and blah, blah, blah. That is the idea. It's not the only idea of green theorem. Some things cannot be done the way we learned it. And then you have to use green theorem or Stokes theorem in upper dimensions. This one only works for 2D and for the closed curves. Questions about this? The formula. The formula is good. Usually students like this formula. They do well in the test when it comes to this formula. And I usually tell you, use green theorem. So the first thing you do when you see the phrase use green theorem, you go to this F and you make a note, P and Q. The moment you start doing that, your brain gets prepared to take derivative of Q with respect to X, P with respect to Y, and move on. So after this, we go to the conservative fields again. Extremely important. And finally, I'll give you some cool ideas of what does it mean to have conservative fields. So let me first tell you again. If P with respect to Y equals Q with respect to X, and there's no holes inside of that D, then for all closed curves, this whole formula gives you 0. So Green's theorem gives you 0 for conservative fields. This is the idea that we had before, remember? Xy equals Yx. So they all kind of keeping this idea. If those mixed partial derivatives gives you the same number, then this whole integral gives you 0. That happens if f is conservative, and vice versa. If that thing gave you 0, if this formula gave you 0, then f is conservative. We had it before. That's actually not new, but now I can give you a strong tool of how to check that f is conservative. Then you can also ask me why it even matters. Why we're so obsessed with f being conservative. If and only if. What does it even mean to have conservative vector fields? That kind of is the idea. Today I will try to explain it to you, to figure out that. Yes?
Sorry, can you go to the thing above the picture?
Here. And no holes. Surprisingly, donuts do not work. If there's a donut, everything gets messed up. Topological properties that got messed up with any holes. 1 hole or 2 holes do not work anymore. So, let me show you this. Intuition is this. We are right now getting finally into the rotations, which we're gonna do after the exam. Curvatures, how things rotate. But actually this integral, this line integral already measures some rotations. Line integral measures the circulation of f around C. So f is some kind of wind. That's the best way to see it. You are on a treadmill, or for example, you are biking over here. So you're biking towards right, counterclockwise, which is the positive direction, usually. Internationally agreed that counterclockwise is a positive direction. And the wind in this case is helping you. If wind is helping you, you remember line integral is positive. If it's very, very positive and big number, it means wind is strong. If it's positive but small number, it means wind helping you, but it's weak. If it is 0, wind is not helping you and not against you. If wind is against you, so I'm biking, it's in my face and it's so strong, I'm a small person, it starts blowing me away, and it's a hustle, to keep biking. Then the line integral is negative. If it's negative and huge, the wind is strong and to my face. If it's negative but small number, it's not too strong. If it's 0, again, doesn't matter. So 0, remember from your homework, was like that. And so on. So line integral gives us lots of information about what the field is doing. And in this case, we talk about wind fields, but it can be electromagnetic fields and electrostatic fields, and I will talk about it right now. So wind or water. Say it is water, I like it more. And this is a whirlpool or rotational properties in the ocean, right? Well, because it's on a closed curve, it tells us what is happening with macroscopic rotations. Macro means big. Micro means small, right? Macroscopic rotations, big rotations. And not big in a matter of size. It's big as a matter of a big picture. When you zoom out and you see the ocean, you see a huge rotational thing in the ocean. You're like, wow, we should avoid that. Or it's a tornado accumulation. You know that. Now, this thing inside zooms in. When you zoom in and you see in the ocean small rotations, they are the one who are creating a big rotation. So this term, dq dx minus dp dy, measures the rotation of f around a point. So you can call it microscopic rotation. Microscopic. So small rotations. Small rotations, like so. So we take small rotations like small whirlpools, right? Looks like from Avatar. And then together they create a bigger rotation, right? So the whole line integral tells you the total movement. But sometimes you want to zoom in and see about microscopic rotations. That's what's inside of the integral, which makes sense. Integral are sums. If you remember definition of integral, wherever dx, those were sums, limits with sums, right? Riemann sums. So we're summing up. Where is my beautiful integral? Here it is. This, can you stop? Yes, thank you, doing that. This is the formula. Green, figure out this formula. So that's why I call green theorem. This thing inside tells us about microscopic rotations in the ocean. But then when we add them up together, it gives you line integral. That gives you macroscopic rotations. So the sums of smaller rotations. Make sense? It's kind of pretty neat idea. I don't sound excited enough about it because I'm sick. But it is pretty neat. Just trust me. It's really cool. So going back here. Here is the idea. Check it out. So this piece only measures rotations around the point. Around the point. Let me mute my phone. Forgot about that. So around one point. So microscopic, microscopic, microscopic. How do they rotate? What if this one rotated like this, but this one rotated like that? What is the total one, right? And you had it in your homework. You saw those beautiful symmetrical rotations in your homework. So what's happening there? Anyway, if it rotates positive direction counterclockwise, then the inside part will be positive. Qx minus py, that's a short notation of partial derivative. You just put tiny x in and everyone knows what it means. Is positive. If it's counterclockwise, well, then it's negative. And if it's not clockwise, it gives you 0. That is the conservative field. Conservative field. Like so. So that's some understanding here. Finally, check it out. This is pretty cool. The green theorem says that if we sum up microscopic rotations, I guess you don't have to write this down, but I feel it's pretty awesome. It equals macroscopic rotations. That's Green's theorem idea. That's why it's pretty genius, Green's theorem. And that's why engineers doing every day Green's theorem in upper dimensions, which is Stokes theorems. It kind of makes sense. Think of microscopic rotations as mini whirlpools or hurricanes in a bathtub, right? So when you're in the bath, you see small ones, but then they create the big movement. So when you add them up, small changes, that gives you a big change. So that's a pretty cool idea here. Does it make sense? I feel like it's pretty cool. So the Green theorem says if you add up all the whirlpools, which look like that, check it out. Whirlpools. If you add up all the whirlpools inside of the bathtub, you get a gigantic whirlpool, or basically circulation around C. So that is the idea here. Big versus small. So the small ones in the bathtub are here and here, but the big one then also creates the rotation. See? And it's bigger on the left because we have bigger, small rotations, and it's smaller on the right. You see? Smaller size because there's a smaller one on the right, and so on. Then I wanted to just tell people, so wait, what is so important about conservative field? Why it even matters? Well, there's a big difference between, you don't have to write it down, between magnetic fields, electromagnetic fields, velocity fields, wind fields. They are different. So the term conservative is related to the concept of conservation of energy. Oh, that one. We all heard about conservation of energy a little bit. But that's actually the connection here. Some forces are conservative. Gravity and magnetism, which means if you travel along a closed path through a gravitational or magnetic field, the initial and final energy will be the same. They're conserved. So it's a closed path, and you drop a metal ball in the magnetic field. Wherever the ball travels, it doesn't lose the energy while traveling. So the initial and final energy will be conserved. Does any of you know this? Yeah? Do you have any your own ways to explain what I'm talking about? I always feel like physics people and engineering people can explain better. Do you want to try?
Well, just if you draw, well, just relating it, so if you draw out gravity as a bunch of arrows, it would kind of, it looks a lot like the non-conservative graph. It's just all pointing down.
All pointing down. Gravity, all pointing down. Yeah, right? That's the gravity of our planet. Good point.
Yeah.
So they're all pointing down. Yeah. So if I drop, if there's a ball in the air and it drops down, its energy being conserved because the gravity took it down, right?
Yeah, it's not really an explanation, but it's like shows how it's similar to
Thank
that.
you. That's good, exactly. However, some forces are not conservative. Or for example, frictions, some wind velocities are not conservative, and so on. So I'm biking and there's a wind towards me. I'm losing energy trying to bike through and so on. So it's not the same thing. Lots of cool stuff. Electromagnetic fields too, also they're conservative. And that's why it's so cool to use this tool to check if they're conservative or not. And also to figure out those rotational properties. What do you think about that? That's actually, green theorem doesn't have lots of homework problem, which is nice. And that's all the material for green theorem. So because I have extra time, I want to show you this. Hope you watched the videos and did some homework without me. But this is what the idea, right? So let me show you that. Last lecture was supposed to be so interesting and I got sick. It was so upsetting. Again, check it out. This is me on the bike, counterclockwise, right? The wind is helping me. F is the wind, or you can see it's magnetic fields, but wind is more natural. Or if it's a boat, then F is the water. It's helping me. Then line integral is positive. And the bigger it is, the more wind is helping me. Does it make sense? That's the idea. If it is 0, that's a conservative vector field. Conservative field. Why it is 0? I'm biking still anyway, counterclockwise or clockwise, but the wind is not towards my face and it's not against me. Doesn't help and doesn't go against me. Perpendicular. Perpendicular means dot product gives me 0. This is a dot product over here. See? Dot product. Dot product is 0, integral is 0. So there's no influence on me biking with that wind. Finally, you can guess. I'm still biking the same direction, but the wind changed direction. Now it's against me. It's negative, and the bigger it is negative, the more it is against me. That is the idea. Some students ask me, yesterday we had office hours. Some students ask me, what is the difference? We have ds, we have dr, this and that. The difference is the formula. So on the test, you will see integral, whatever is inside, f ds, and you will have integral f dr. Your job is to know the difference. So f dr is a line integral over the vector field. Dr says find r prime. That's kind of how you remember. So the tail is different, tail matters. So the only difference is, you remember that, oh, they want me to differentiate r and it will be dt. And also we are integrating over the vector field. How about ds? Who remembers what ds is? It's not over the vector field. It is over the curve. We're for the first time integrating over the curve. So it has connection with arc lengths because it's the curve. This is like wind. R primes are collecting strengths of the wind I was just talking right now. While this ds is arc lengths, because it's like a wire. We're integrating on top of the wire. So that's why the formula has connection with the arc lengths. What's the formula? ds. What?
Square root of 2
Derivative squared.
Or 3, like x derivative squared.
X derivative squared. Y derivative squared. If needed, z derivative squared. If it's high dimensions and so on. And times dt. Right? Or not? And you can also, some people call it, you still find r prime, right? But then you take magnitude of that. That's also, how cool is that? So it's still r prime. But unlike dot product that we have in the line integral, f ds has arc lengths. So its arc length is a number. That is something I wanted to talk about. Bless you. And I also wanted to mention this. What does it mean to have line integral in general? Integral f dr, line integral f dr. So when I'm biking, again, and there are different kind of wind, like this, like that, the wind is messed up, kind of collection of many different winds. When I bike and I want to find line integral collects all of those errors. So when I'm biking, it's like a computer game. It collects this one, and then it's recorded. Oh, it's perpendicular, doesn't matter. Then it collects this one on the way. Oh, that's towards my direction, helping me, but a little bit, because it's not completely there, it's a bit to the left. 0, 0, against me, to far, close. So it collects the arrows on the way of my path. The final answer of the line integral will be positive. Oh, total wind, even some of it was into my face. Total wind is helping. Does it make sense? If the final integral result is negative, even though at some point it was helping me, most of it was into my face. If it's 0 or small and close to 0, most of it is perpendicular to me, so I don't care. So it's like a computer game. You travel on the curve and collect all of those errors on the way. So in this case, all the errors are pointing to the left. That's from your homework, right? At some point, they're helping me. Right now, they're helping me. But now I'm turning direction. They're into my face. When I go up, they're perpendicular. So what will be the total? If the total is positive and huge, most of them are helping me. Does that make sense? That's the idea. So that's why it's a very important tool. It sums up or integrates. That's the same word. Values of f along C. And f is a field. And that's why you just need to remember this formula. So that's for your homework. And then I think there was something cool to show you. And let me show you. Did you watch how to find potential function without me? Yes.
So how can you decide whether or not to use the line integral or to use the Green's theorem? Is there like a way to tell?
Good question. Green theorem is easier. So actually everyone switched to green theorem at some point. We just teach you both right now. Remember, it's like a product rule, quotient rule, and then boom, we like jump to chain rule, and now we switch to chain rule most of the time. Same thing, different methods, but also green theorem doesn't work in more dimensions than 2. So in this class, we don't know what to do in upper dimensions, and that's why we have to use line integrals. But in general, it's just the accumulation of material. It's a very smart question, yeah. And it tells you how to learn, how to know what is going on, where the whole idea came from. Did you watch the video without me? Oh, about the potential function. How to find potential function. You need to recognize this term, potential function. Did you watch that? And I'll show you right now, because it's going to the test, so I would like to make sure you know that. And then we're going to do the quiz. So this piece, check it out. I also like this explanation. Derivative of p with respect to x and derivative of q with respect to y. This is the comparison of a flashlight. When there's a flashlight from the right, the shadow of this fence looks like this. When there's a flashlight towards this direction, the shadow will be here, and it's different. So depending with respect to what we're differentiating, that gives different shadows. Collecting them together gives you the total perspective. That's a pretty cool idea of seeing it. Shadow means projection or a domain. So with respect to on the x-axis, it looks like this, but on the y-axis, it will be shorter. So total give us the total idea of the fence. I like that a lot. This is a pretty cool idea of the flashlight. Okay, let's do one potential function. And with antiderivative. I thought it was here, and it's not. Find f. Okay, so potential function. It can go to 13.4, but actually it's 13.3. Potential function. It doesn't matter too much. The material right now is very fluid, so all those 3 chapters are very connected. Potential function is a function f such that f equals derivative of f is f. F equals derivative of f. Oh yeah, I'm correct. So only works for we're working on conservative fields. Conservative potential function. So basically we want to integrate my f. Capital F is the wind. Derivative of small f is how strong the wind is, right? So the idea is, okay, if f is already a speed, what is the integral of speed? Distance, right? So I would like to know where the wind is located and how big it is. What was the original function, f, that we integrated to get capital F? No, differentiated to get capital F. This sign is a fancy sign for derivative, right? It's a gradient. Gradients, derivatives, all of them collected together. So this is the idea. There's a wind, and I see how big it is. It's definitely like in that room, but not in this room. That's distance. Then I want to know how strong the wind is. I differentiate wind pieces, which are vectors. Here, 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 everywhere. Towards all directions, x, y, z, and so on. And I get capital F, and that's called a vector field. And now it's a field representing the wind. What if I only see the wind, and we have devices recording the wind speed? Can I find out where is it located? That's literally the basic idea of earthquakes and stuff. If F is a magnetic fields or tractions, frictions, I want to know where the earthquake is located. That's going back, integrating. That's possible for conservative fields, so let's do that. Example, let's see. Find the potential function. The potential function f such that when you differentiate f, it gives you capital F. That's A. And B, calculate or find integral over CF dr, where F is sine y, x cosine y minus sine y, and C is the line from 0 to 1 pi. This is a very classical free response question for the exam. It has it has A and B. Each A and B has like steps and stuff. So I need to make sure you know that. This is like super important. Potential functions, sometimes just by themselves, they go to multiple choice, but that's whole thing, it's like a perfect free response question to grade. So usually it's very classical choice for, even for final exams. We quite often put it there. So first step is to find potential function. Second step is to actually calculate the line integral. Solution. To find potential function, we need to first answer if this field is conservative, or else we cannot do that. Question mark. To check that, we have this property, differentiate P with respect to Y equals Q with respect to X. That's the question mark. Or just right now we learned 1 minus another one gives you 0. Well, that's the same thing. So is it conservative or not? Where is P? Where is Q? F consists of P and Q. Don't freak out, just mark it. And now we can proceed. Let's check. So I'm first differentiating second component, Q. Well, usually people start with Q. Usually people start with this one because of the Green's theorem. So it's a good habit. Second component with respect to X gives you X cosine Y gives you what? Cosine Y minus sine Y gives you 0. So it's just cosine Y. I will write down. Second component with respect to X is cosine Y. Let's check the first component. The first component with respect to Y, sine Y gives you cosine Y. Yes, it's a conservative vector field. Since I'm not contagious, just like letting you know one more time, I asked. Since these two guys are the same, then F is conservative. And we can find, the potential function F such that derivative of F gives you the vector field capital F. So it's called potential function. Did I mention it? I kind of keep using this term so vaguely. But potential function F. We don't have to have all of them. We just need to have any. That's why it's called potential. Any that fits. I will explain in a second why it's any. So step 1, just to check the situation. Step 2, let me do step 1. Step 1, we checked that we can actually perform the procedure. Step 2, now we start the procedure finding of potential function F, small f. And the book explains this kind of in a hard way. I feel like I'm teaching it easier. So when I showed students, they're very surprised that it's much harder when they watch ASU videos for some reason. So I like this way better. And it's correct. So we're gonna start finding anti-derivatives, basically integrating. Step 2, find potential functions by finding anti-derivatives. So if capital F comes from derivative of small f, we need to integrate. Integrate what? I'll put it in new color. F is given as sine y, comma, x cosine y minus sine y. That, so given, we have that. We will call that partial derivative with respect to x and partial derivative with respect to y, because that's what gradient is. That's definition of the gradient. And we have, if we have third variable, partial derivative with respect to z, and fourth variable, partial derivative with respect to t, or whatever variables they are. So we have derivative with respect to x is this first term. So f with respect to x is given as sine y, and f with respect to y is given as x cosine y minus sine y, like so. Does it make sense? Let me color code it. Isn't it fun? People like, what? So we have equation 1 and equation 2. We know how to integrate from equation 1. F that depends on both variables will be integral of sine y with respect to what? Guess. How do you know it's x? Because of this guy. See? This tiny subderivative tells us what differentiation was performed. So now we have to undo it, bless you. We're undoing differentiation. So what is the integral of sine y with respect to x? X sine y. Correct? Something is missing? Plus c. And this is where the book makes it different. You can check how they're doing it. C is not just a constant here. C can depend on y, because derivative of y with respect to x is also 0. But I don't care. I just write down plus c. Let's do the second term. Also, x and y, this same function can be found from integrating the second equation. Integral of x cosine y minus sine y with respect to what? dy, because it says it was derivative with respect to y. Okay, that looks harder. Let's see. X cosine y integrating with respect to y gives you what? X sine y, plus or minus? Plus, because derivative of sine is plus. Good job. Minus sine y with respect to y. Integral of sine gives you minus cosine. Minus gives you plus. Amazing. Plus c. But it's not the same c. So let's call it k. Some people call it c1, c2, if you want. c1, c2. Doesn't matter because they will disappear right now. This c can depend on x, because we're differentiating with respect to y. So whatever x squared, for example, with respect to y is also 0. And now check it out. You collect the repetitive terms and don't count them twice, and then add the extras. Duh, that's it. The way in the book, this is so much more complicated. You'll see it's so much longer to do. So what we're going to do is we're going to conclude. This should be the same function. Thus, f of x comma y will be x sine y. Don't repeat it twice. It showed up twice, so it's there. Plus cosine y. And of course, plus some kind of big C, which we don't care about. We just need some kind of function. It's called potential function. We don't need all of them. One is good enough, so c equals 0 is good enough too. So note, what I'm doing here is we don't double count. We don't double count terms. We need only one f. So there can be more than one, but we need just one. So we're fine with this one. You can check if you differentiate it with respect to x and y, you will get a gradient. So this is already good stuff to grade on the test. Okay, this is a really good piece to do. Why did we do that? Because using antiderivatives is also helpful to calculate line integrals. Third step, well, let's actually B. So whatever is in this box answering A, that's called potential function. Potential function for the given function, for the given f. We integrated it and found it. Now they want us to actually find line integral. Line integral over C, f, dr. We know the formula. It's over C gradient f dr. But we just found f by the fundamental theorem of calculus. We take f of the end minus f of the start. That's what's happening here. F of the end minus f of, just like f of b minus f of a. In this specific case, we take my small f and plug the end point and plug the beginning point. Did they give us those points? It says the line is coming from 2, 0 to 1 pi. So 2, 0 is the start, 1 pi is the end. Now you plug into the function we just found. And that gives you the answer. Use A. We will use the function of A, and it gives us sine pi plus cosine pi minus 2 sine 0 minus cosine 0. Minus or plus? Let me check. Plus. We plug it into function we just found, and it gets us the answer equals minus 2. So we did not do parameterization like we did before for the line integral. We just used fundamental theorem of calculus. If you know the original small f, why bother finding line integral with using the formula if there's a f of b minus f of a thing? So that's the same thing we learned. Remember, integral, whatever, I will not write it down. That will confuse you more, I think. Fundamental theorem of calculus says, if you know the antiderivative, plug the top minus the bottom. In this case, it's more complicated because it works with line and the vector fields. If you know the small f, which is called potential function of the vector field, then plug the ending point of your traveling, because it was traveled, minus the beginning point of your travel. So B says we traveled from 2, 0 to 1 pi and minus the beginning. What do you think about that? Not too bad. Definitely lots of material before the test. Exam 3 has lots of stuff to cover, so please don't postpone. Start preparing as soon as possible. I posted the practice exam for you. Everything is ready. You just need to, I'm not saying it's simple. I never do that. But because it's not simple, you should not assume you will have lots of time for that. One problem for the exam 3 probably takes like 3 problems for the exam 2. So you need to kind of have more time because it's a challenging material. Does it make sense? One of the cases of, for example, magnetic fields. See, if you have a piece of paper, it stretches. Because the farther you are from the center, the stronger the field is. How cool is that? Okay, I think this is good.